When it comes to projectile motion, specifically horizontal projectile motion, there's a few things that if you understand, you are going to solve these with a much higher success rate. What you see in front of you is a pretty straightforward example. You're given an object that rolls off or is launched from some speed off of a cliff or a table or something like that, and you're asked to determine how far away horizontally will this land from its launch point. We need to understand that most of these are going to take place on Earth. Unless otherwise specified, it's safe to assume they're taking place on Earth. So you will always know automatically that the vertical acceleration is negative 9.81 meters per second squared. There is no natural force that just like accelerates objects in our universe. There's no horizontal gravity, for example. So a true projectile will have no horizontal acceleration. To accelerate horizontally, if you're flying through the air, you need an engine, you need like thrusters, and that puts another force on you other than gravity. So you're no longer a projectile if that's the case. So to be a true projectile, you cannot in any way have any other forces acting on you other than gravity, which means the only thing that can act on you is gravity, and gravity acts vertically. If nothing else can act on you, then there can be no horizontal forces to speed you up, slow you down, etc. The other thing to understand is that for a horizontal launch, your initial vertical velocity is 0. I'm going to try and maybe explain that in a little more detail. We basically have three options. You could kind of kick this thing or launch it upwards at some angle. You can launch it straight out like we do in horizontal launches, or we could kind of throw it downwards at an angle. What I want to point out here is that if I launch it upwards, you're doing two things. If you're firing upwards at an angle, you're firing it outwards, but also upwards. If you're firing it downwards, you're firing it outwards and also downwards. So I want to highlight here that for an angled launch, you do have this vertical portion of your starting velocity. You're launching upwards a little bit, or you're launching it downwards a little bit. You don't have that when I have a horizontal launch. You can't form a triangle out of a line that's just on the x-axis. So that's why we have no vertical initial velocity. And that's why VIY for these horizontal projectile problems is always going to be 0. As we start to look at situations like this or this, where you are launching at an angle, that is no longer true. But for horizontal projectiles, it's a little bit of a simpler case. We don't have any of those vertical components initially, so we can ignore everything and say it's 0. And lastly, the time, since this is one event, is always going to be the same for both the x and the y. If it takes this cannon 7 seconds to follow that path, well, it took 7 seconds to drop 90 meters, but also 7 seconds to travel out whatever horizontal distance it ends up traveling. All right, as always, I recommend we make an XY table when we want to analyze these questions. So we'll keep the horizontal and the vertical separate. So we've got an initial, a final, an acceleration, a displacement, and a time for both the horizontal and the vertical components of this motion. All right, we'll fill in, we'll do delta y in that case. We'll fill in what we know. So horizontal launch, so 25 meters per second, because that's entirely horizontal. And vertical is always 0 initial for the reasons described down below. The acceleration for a true projectile horizontally is always 0. And vertically, since this we can assume is Earth, is negative 9.81. And in this case, it drops 90 meters. So I have to say vertically, it lands 90 meters below where it started. If you don't put the negative, be careful. You wind up with like a negative time. You get really excited because you think you invented time travel. Turns out, no, you just embarrassingly misapplied your algebra. Everyone laughs at you, and you don't even have a time machine to go back in time and fix your mistake because, as we said, you didn't just invent time travel. You just messed up algebra, like Mr. Walkovich does quite often. At least you didn't do it in front of a class of students who you're supposed to be the expert in the room, because trust me, that's embarrassing. All right, back to the problem. I've got 3 variables on the y side, 2 variables on the x. That means the y side's probably a good place to start. I could find the final velocity, but that's the one I'm not really concerned about for the moment, because I know that time is the factor that they both share. So if I can find that, that will give me my 3rd variable on the x side. So that gives me this equation, delta x equals VIT plus 1/2 AT squared. I could use any one, but this is the one that doesn't have VF. This is the one that's going to help me find what I need. Initial velocity is 0, so I can just cancel that out. And to be fair, I should probably write delta y. So negative 90 equals 1/2 times negative 9.81 t squared. So I'll just do all the steps. Negative 90 equals negative 4.905 t squared. If I divide both sides by negative 4.905, I'll do all the steps this time, and then in the future sample problems, I will just kind of show you the end result. So if I divide that, I get 18.35 about equals t squared. Take the square root of both sides. Time equals plus or minus, because that's what you get when you take a square root. Square root of that is plus or minus 4.28 seconds. Now, unfortunately, as we said, we didn't really invent time travel, so we can go ahead and we can get rid of that negative. We know that the actual amount of time has to be 4.28 because negative time makes no sense. Now I've got my 3 variables on the other side. I'll write this in blue. So if I take these 3 variables and I do my work down here, if I want to find delta x, well, delta x equals VIT plus 1/2 AT squared again. I like this equation because 0 acceleration means this is gone. So delta x just equals VIT. So delta x equals my initial velocity of 25. My time is 4.28. So this thing must have gone about 107 meters. All right, I know I kind of scribbled all over the place here, so I apologize, but I do want to point out these important concepts are all that I use to basically get all the variables that I need. All right, so let me show you another example or two. I got a similar situation here. I will just kind of go through how to solve this one, maybe a little bit quicker. All right, so I'm going to make my XY table here. I generally do this for each question. It takes a little bit of time, but makes things quite a bit easier to analyze. All right, this is a horizontal launch, so I know right off the bat 0 for the vertical, and all 18 is applied in the horizontal because that's how it was launched. 0 acceleration horizontally, negative 9.81 because we can again assume this is Earth. In this case, I know it travels 150 meters in the X direction. I don't know enough about the Y, so I'm going to flip this one, and instead of starting with the Y, I'm going to start with the X. Again, time is the key I want to find. So once again, final velocity is, again, I could find it, but that's the one I don't really care about. We will find that this equation we use very often of the 5. So we know here that that goes away because you have no acceleration. So 150 is my initial, which is 18 times time. So divide both sides by 18. And I get about 8.33 seconds. I can put that in both locations. Now I've got the variables I need to solve the y. And again, I want to find delta y. I don't really care about VF, so as I said, this equation kind of pops up quite a bit. And it's nice that it pops up quite a bit, especially with horizontal launches, because I know with horizontal launches, in this case, I have no initial velocity, so that piece is gone. So delta y equals 1/2 times negative 9.81, and we know my time is 8.33 seconds, and I square that. If I plug all of that in, we've got 1/2 times negative 9.81 times 8.33 squared. And that gets me 340.4 meters negative, because that's the displacement. So the height of that cliff is 340.4 meters, or we can say the ball drops 340.4 meters. By the way, that's what I was looking for. I didn't really state that at the beginning. All right, I've got one more for you, a little bit different. This one's going to take place on the moon. So I wanted to show you what happens when we don't have negative 9.81. And also, I kind of just wanted to draw that little astronaut guy because he's kind of, I think he's adorable. Anyway, if you don't think so, keep it to yourself because I don't need to cry myself to sleep tonight. All right, so this astronaut is on the moon. He decides to like throw a lunar rock into some crater, and he's going to try and figure out how tall is this crater. This is not the most scientific method. But if he throws it and he has a general idea of how fast he threw it and he can estimate how far it went, he absolutely can get a pretty good estimate of how high this is. So he's going to throw it at 16 meters per second. The difference here is on the moon, gravity is significantly weaker. So instead of negative 9.81, we are told that it's negative 1.67. It's about a sixth, I believe, of what it is on Earth. All right, as we do always, I guess I'll do it down here, give myself some room. We're going to set up our XY table. All right, VI, VFA, delta X, T, VI, VFA, delta Y, T, and then let's go ahead and populate this. Again, this is still a horizontal launch, 0 initial in the Y, all 16 is that in the X. Projectiles do not accelerate horizontally. In this case, I need to put negative 1.67, and 80 meters is the horizontal displacement. All right, so what we can do here is we've got 3 on the X side, so let's do what we normally do. Use the X side to find time, move time over, find what we're looking for. So if I look at the X side, again, I don't really care about final velocity. Time is what I'm looking for, so once again, this equation comes to the rescue. And as I said, I really like this equation because that just goes away because there's 0 acceleration. So in order to go 80 meters, being thrown at 16 meters per second, I'm just going to take 80 divided by 16. Probably could have done that one in my head, but 5 seconds it will be in the air for. I can then plug that down into my Y table. So 5 seconds. Again, final velocity, don't care about it at the moment. This is what I'm looking for. So once again, this equation comes to the rescue. We're going to use this one quite a bit. All right, let's plug in what we know. Well, first of all, 0 initial velocity means that that piece is gone. So delta y equals 1/2 times my lunar acceleration of negative 1.67. And we know that that was in the air for 5 seconds. So as a rough estimate, assuming these values would be correct, 1/2 times negative 1.67 times 5 squared, which is 25, we get negative 20.88 meters. So the height of this, I just wrote a lowercase letter on accident and it was actually painful. Oh, we're going to make that a capital. I apologize. That was disturbing. The height is going to be about 20.88 meters because we measure height from the base to the top. All right, if you remember those key concepts, you should find that these are not that tricky at all. And even when we add the angled launches, if you fall back on your core concepts, you're going to find you do just all right. Good luck.